Okay, let's do an example of a set of level curves. Function f of xy equal x squared plus 4y squared. First, we'll note that for any values of x and y, this function is non-negative. Can't be negative squares. Sum of positive multiples of squares can be at the least equal to 0, and the only point at which that occurs is where x and y are both 0. That's the origin. F of xy equals 1. Well, that's straightforward. That's just an ellipse with a major axis of 1 in the x direction, minor axis of 1/2 in the y direction. And I'm not going to work out the details of how we get that ellipse. This is something we've seen repeatedly by this point in the course. So if necessary, review your conic sections, but straightforward to determine that this is the ellipse that I've sketched here. Now, if we go to f of xy equals 2, well, that's x squared plus 4y squared equals 2. That's 1/2 x squared plus 2y squared equals 1, and that would be x squared over square root of 2 plus y squared over, it'd be 1 over the square root of 2, which would be square root of 2 over 2. And I'm not going to go through the rationalization of that denominator. I'm simply going to say that that's an ellipse that has major axis square root of 2, a little bigger than 1, about 1.4, 1.414. So we're getting a bigger ellipse. It's not twice as big. This number is twice as big as this, but the ellipse doesn't have twice the dimensions of the other. It does have twice the area, incidentally, but not going to. Okay, so if this is 1 and this is -1, then our ellipse is going to come out to about 1.4 over here, to about -1.4. It's going to be about half that great in this direction. And without labeling it, I'll simply indicate that we get an ellipse of similar, geometrically similar shape to this one, but bigger. Square root of 2 times as long, square root of 2 times as wide, and we can worry about the details of this. But the picture that emerges is a set of level curves. And let's go to slightly smaller scale. Let's put 1 here, -1 here, 1/2 here, -1/2 here, and draw our c equals 1 curve. That would be f of xy equals 1, and that's this curve. Our f of xy equals 2 curve, well, it's going to be about 40% greater in both directions. Values of x and y will be about 40% greater. Didn't do a very good job at that vertex, and probably not doing a very good job at this one. But we see that this is f of xy equal 2. Now, f of xy equal 3 will be a slightly bigger ellipse. F of xy equals 4, and we can actually kind of sketch at least part of that one. If we come out 2 units, we're going to end up about here and about here, and don't have a lot to be proud of with my scale here, but this would be our f of xy equals 4 curve. And the f of xy equals 3 curve is going to lie in between here. So we see a series of level curves. Now, I've taken a little more care with my sketch. It's still not great. I'd be better off if I was able to draw the rectangles and the tangents and so forth. But we see that I have here the curve f of xy equals 1 and the curve f of xy equals 2. Based on just this sketch of the 2 level curves, I can sketch something of the behavior of the gradient function at points along the first curve. Now the gradient is going to be perpendicular to the curve, so when we're close to the intercept with the x-axis, the gradient is going to be pretty close to the x direction. It's going to be tilted up a little bit, and that should be clear. In other words, the direction tangent to the curve is here, so our gradient is going to be out here. And let's just draw that at some arbitrary length. I've exaggerated the slope of this thing somewhat, but you should get the idea. So if I draw a gradient here, it's going to come out in this direction. I'm not drawing the whole gradient. I'm just going to draw the tangent line and the direction. If it's here, it's going to be kind of out in this direction, a little bit away from the y-axis. Here, tangent direction, direction of the gradient, tangent direction, direction of the gradient, and that's going to continue all the way around the curve. Let's ask what's happening to the gradient as we move around this curve. What's happening to the magnitude of the gradient? Well, to get from value f of xy equal 1 to value f of xy equals 2 required this much distance here. Now these curves get closer together when we get up toward the y-axis. Matter of fact, at the y-axis they'll be twice as close together as they are here, and it should be fairly evident why. So that the gradient at this point should be about twice as big as the gradient at this point, almost twice as big, because the curves are almost twice as far apart here as they are here, meaning that the function has to change much more quickly to get from f equals 1 here to f equals 2 here. So if the gradient vector is this long here, it's going to have to be about twice that long here, and if I sketch it, it's going to look maybe something like this. Now my y-axis isn't particularly straight, so it doesn't look that good, but the gradient is larger when the level curves at equal c increments. Kind of slopped over that word there, but you see what I mean, are closer. Okay, so the gradient's larger here because the curves are closer. Gradients are smaller here because the curves are not as close, and I think I could have drawn that quite a bit bigger. But it should be clear that this is somewhat larger than this. And at the intermediate point, the gradient is going to be somewhere between this length and this length, maybe about like this. Of course, we could draw these things to scale, but we get the idea that the gradient is, that one's actually longer than this, and that won't really happen. And then this one will be somewhat shorter. Now let's see if this behavior is borne out by the calculations. The gradient of f is partial with respect to x times I plus partial with respect to y times j applied to the vector. It's x squared plus 4y squared, but I started writing the 4 a little bit early, so we're going to live with that. And the partial with respect to x, it's just going to be 2xi, and then it's going to be plus 8y times j. So, not a difficult calculation at all. Remember that the direction of the gradient has to be the direction of this vector here. When x is large and y is small, then this vector the j component is small, and the vector will be pretty much in the I direction, which agrees with what we have here close to the x-axis. And when x is small, the vector will be close to the j direction, which occurs up here. The magnitude of the gradient reveals how quickly the value of the function changes as we move in the direction of the gradient. So if we calculate the magnitude of the gradient, we find that that's the square root of 4x squared plus 64y squared. The coefficient of y squared is a lot bigger than the coefficient of x squared. Of course, y can only get half as big as x can, so that the largest y is half as big as the largest x, so the largest y squared will be a fourth as big as the largest x, so that the relative contributions of these terms are not as extreme as it might seem from these two coefficients. And then when we take the square root, well, we can confirm from this expression that the magnitude of the gradient as we approach this point is twice as great as the magnitude at this point. Specifically, we can say that the gradient of f at the point 1, 0 on this ellipse is easily evaluated. Y is 0, x is 1, so we get the square root of 4, which is 2. The magnitude of the gradient of f at 0, 1/2, which is the y coordinate that's most distant from the origin, is the square root of 64 times 1/2 squared, which is the square root of 16, which is 2. In general, I'll leave it to you to verify that the gradient of f at any point a0 has a magnitude that's twice as great as the magnitude of the gradient of f at the point 0, 1/2 a. And you can think about how that would apply to the level curve picture for this function. Another aspect of the level curve picture that I haven't included here, when we get up to f equals 4, we're only out to this point and this point, and f equals 3 is going to be in here somewhere. What we're going to see is that the f of xy equals 3 level curve is closer to the f of xy equals 2 curve than the f of xy equal 2 curve to the f of xy equal 1 curve, so that as we move out from the origin to curves for increasing values of our constant c, the gradient gets bigger and bigger.